Okay. Yeah. Hello everyone. Do you have any questions?
Yeah. Yesterday we saw the method of images.
Mhm.
I wanted to ask, can we generalize it for more complex structure? Like we saw it for a charge. Can I, for example, do it with a line segment or a line, infinite line, or maybe a circle?
Do you mean charged line or? Uh, oh, but it's different. If you want to find a field created by some charge line, you just need to take a corresponding green function and integrate over this line, because how to produce it using method of images. So it's something of this kind. For example, uh, so, by the way, sorry, the last time I was writing green function of Laplace operator with the wrong sign. It was green function of minus Laplace. I'm always confusing them. So, green function of Laplace is just a logarithm. So, um, 1 over 2 pi, 2 pi logarithm of absolute value of z equals to delta of x minus delta of x, delta of y. And for higher dimensions, for 3 dimensions, it is Laplace of minus 1 over r equals to 4 pi r equals to delta of r. Sorry, it was a mistake yesterday. Mm, when I was in the evening. Uh, okay, so a charged line. Suppose that it goes from 0 to some a, or to 1. Maybe it's all the same. Maybe, well, to a. So there is some linear charge here. So to compute potential, let us write some formula for this charge distribution. So it will be x, y, x. And z is x plus I, y. So we are solving an equation. Laplace of phi equals to rho. And who can tell what is the formula for this rho? Hmm? Mm, 0 and a. Well, it should be some different x, because it is a function of x. Mhm. Mhm. Uh, Yes, it is fine, but now can we integrate, can we compute this integral in x prime? So what will it equal to?
It should be theta y times.
A theta of, oh, so it's something that is non-vanishing when x is between 0 and a. So it is some theta of x minus a minus theta x. So theta of no theta of x minus theta of x minus a. So this is step function times delta of y. So it's something intuitive. It is something that has a non-trivial amount of charge per the unit line.
So it's basically the characteristic function of the segment times delta y.
Yes, yes, of course. So, and if you want to write u of xy, it should be what so if we now say that Laplacian of phi of xy, so if we say that Laplacian of phi of x y equals to rho, then like Laplacian g of x y, or maybe let me simply write the formula and you say if it is clear or not. So phi of xy will be the integral from 0 to a, 0 to a, dx prime, green function of y minus 0 and x minus x prime. Is it fine? So we are integrating over. So we can write it as a double integral. We can write it as the integral over the whole space dx dy dx prime dy prime over R2 g of x minus x prime y minus y prime a row of x prime y prime. This by definition. And then we substitute this formula for a row. So y prime integral can be computed immediately. So and we are left with the integral in dx prime over r, this theta heavy side of x prime minus theta heavy side of x prime minus a times green function of x minus x prime y minus 0. And so and this integral is the integral from 0 to a dx prime g of x minus x prime y. Is it fine? Okay, so and now let us take this formula for g. from this grand function. So let us write it like as phi of z. It is 1 over 4 pi integral from 0 to a, from 0 to a, logarithm of z minus x prime plus logarithm of z bar minus x prime dx prime. And so integral of logarithm should be so it is maybe it is easier to write it in the opposite way, x prime minus z x prime minus z bar, so that it's easier to integrate it, and we don't need to think about signs. So to compute the integral of the logarithm, we need to check that z log z minus z prime equals to log of z. So we simply differentiate it and see that oh no, what did I write? Z minus 1 log of z. No, sorry. No, it was fine before. Z log z minus z. So when we differentiate z, we get log of z. When we differentiate log of z, we get 1 over z, which gives 1. And when we differentiate z, we get minus 1. So this is the integral of the logarithm. So it is 1 over 4 pi. This x prime minus z log of x prime minus z plus x prime minus z bar log of x prime minus z bar. And the last term is 2x prime minus z minus z bar. And this changes from 0 to a. 0 to a. So this constant will vanish, and the expression we get is 1 over 4 pi. Like this, and actually it is simpler to write just a real part of this function, because we see that there are conjugate pieces in this expression. Actually, here it should be. No, it's fine. Mm, here it is minus d log z minus z. So it will be minus 2x prime plus z plus z bar. But this term does not contribute.
Yeah, but 2x prime should be there.
Mm-hmm.
Okay.
Yes. Thanks. And we can write it as a real part of this function. A real part of yes, of this function minus minus a. Okay.
So basically, if I have with distribution of charges, I just use superposition on the green function.
Mm-hmm.
Okay.
Yes. So a method of images is adjusted for different kind of problems where we have some non-trivial boundary conditions, and we want to solve these boundary conditions by creating image charges. So, and I will show some other configuration that can be used by more complicated systems of images. So, uh, so basically, I want to tell how to obtain Jacobi theta functions from electrostatical problems, and also apply them to the heat equation. So. We probably wanted to say something about this or not. Yeah, no, so there is some remark about this expression because we get some logarithm in the answer, and this logarithm is some homomorphic function which is not single valued. It has some jump. So the point is that this jump of logarithm appears precisely where we have this charge distribution, which is of course natural. So for example, if we write some different integration contour here, I know maybe it will not work this way for different contours. No, I didn't think about different contours. Maybe. So I didn't check, but probably if I choose some different contour, we will have a similar answer, but with a differently chosen branch cut. Is it true or not? No, maybe it's not true because here this dx prime should be real, and we could integrate this function just because it was real. We just need to know that branch cuts of these logarithms line on the real line and produce precisely this jump between 0 and a. Okay, so now about some more advanced configurations that can be solved by this method. We already solved this problem with the upper half plane and some charge in here. So it's solved. Let us try to solve some problem with two uh, uh, boundaries. So we ask u of x0 to be 0 and u of xy to be 0. I only put some charge here at point x, well, at point z. So now to get this boundary affects L. So it is 0, it is L. So to get these boundary conditions, we need to add charges at this point. It will be z bar. Let us call it z0. So this point will be z0 bar. And let us denote the charges. And this one will be plus, this one will be minus. Z0 bar. So what else? We also need to reflect with respect to this line, and it creates a minus sign, minus charge. So this is 0, and this is L, and this is minus y0, this is y0. So I'm saying that this will be 2L, so this will be 2L, and this will be 2L plus y0. So sorry, not plus y0, but minus y0. And here we will have a charge at point 2L plus y0. So is it fine? And we continue this infinitely in both directions. So plus charges are located at points y0 plus 2kl for integer case, and minus charges are located at minus y0 plus 2kl. Right. So we can, so naively, we can write that green function will be such a product over. So it will be 1 over 2 pi logarithm of product over integer case. Y minus y0 plus 2kl divided by y plus y0 plus 2kl. Absolute value of this. Or we can rearrange this charges. No, it doesn't matter. Then we can group them somehow. And in principle, there are some such infinite products that can be computed. So, namely, we can rewrite this as a product over a positive case. Maybe. Maybe let us leave it as is, but try to write it as a function that has zeros and poles at this point. Absolute value of do you know? It will be some function of function of function f1 of y divided by f2 of y. Can you write a function that has zeros precisely at these points? Yes, you can write like this. Let's actually do this. Let us write sine of what? Of y minus y0 divided by or multiplied by something. Maybe pi y minus y0 divided by by 2l, I think. Right? Because when we shift by 2kl, it is shifted by pi k, which only changes its sign. So, and divided by sine of pi plus y0 over 2l. Right. And there are actually infinite. There is actually infinite product formula for sine, which is obtained precisely in this way. We know all zeros of one function, we know zeros of another function, and we know that this product can be written such that it converges. We divide them, say that it is some holomorphic function that goes to 1 at infinity, and so it is identically 1.
Without the logarithm?
Oh, sorry, log. Of course, it is here. Yeah, so well, there is such function And
This function, where this function are having 0, y minus y naught plus 2k is.
yes.
When y is equal to this, y naught plus 2k it is having 0 or I'm not understanding. Okay, if you have this function, what let's say f of y is equal to y minus y naught plus 2k. Yeah, not
Yeah,
above.
yes. So this is. Hmm?
This where this function above this. Yes. So where this function is having 0 according to your equation.
At all points y0 plus 2kl or some two times integer number times l. Oh, one question. So these are all integer numbers. So we write all zeros in the numerator, all poles in the denominator. And, yeah, yeah. Mm. Oh, actually, wait. Uh, what what did I write here? Uh, uh, so this should be imaginary numbers actually. So sorry, how to write this? So all this should be multiplied by I because imaginary axis goes in that direction. Mm. So sorry, I'm adding here an imaginary unit everywhere, and this y should be z. It is our complex coordinate. So and this formula should be should be modified. It is a hyperbolic sign of z plus uh, plus I over 0. No, sorry. Uh, I missed the direction. So is it fine? Ah, yeah, yes. Thanks. Here. It's basically a 90 degree a 90 degrees rotation. I just missed real and imaginary parts. Uh, and let us look at the behavior of this gain function. So let us see what happens when z goes to plus or to minus infinity. So this gain function is 1 over 2 pi logarithm of absolute value of let us write this hyperbolic sign in terms of exponentials. So it will be 1 minus e to the minus pi z minus I by 0 divided by L. And this will be e to minus pi z plus I by 0 divided by L. So so if you now substitute x and y, it will be 1 over 2 pi logarithm of so its value of 1 minus e to the minus pi x over L e to I pi y minus y0 over L divided by 1 minus e to minus pi x over L e to minus a pi y plus y0 over L. And so I don't want to expand it further, but the point is that this again function behaves like e to minus pi x plus times some coefficient times plus e to the minus 2 pi x times some coefficient plus and so on. And in principle, if you remember our previous methods to solve such problems, namely using normal modes, we can apply such methods also here. So what will we need to do? So we have y coordinate. We have x coordinate, and we have this interval from 0 to L. So we can write and we have zero boundary conditions. So we can write u of x and y again as a partial Fourier transform in one coordinate. But since there are those zero boundary conditions, it should be a signed Fourier transform. So we say that this u of xy is a sum of Cn of x sine of pi and y over L. Right? So there are functions that vanish on both ends from n equals to 1 to infinity. And if you now substitute it into this equation, then what will be the equation satisfied by this Cn's? So the Cn 2 primes of x will be what? Let us call it un maybe. Un tilde.
In terms of what? Of u or in order to verify the class equation?
Yes, of course. So we are solving a class equation. So u xx plus u yy equals to 0.
Yeah, so maybe u double prime minus times sine of pi n y whatever.
So
Minus phi n over L squared.
Oh, sum over n's, right?
Yeah, and phi over n over L squared.
Mm-hmm.
Cn sine.
Yeah, of x sine of pi and y over L equals to 0, right?
Okay. So
So
yeah, so is u double prime equal to pi n over L squared un.
mm-hmm.
Okay.
Yes, thanks. So it's again a separation of variables. Mm. And so now if you know that some function goes to 0 when x goes to infinity, mm, so the only solution of this equation that has this property is un tilde equals to un of 0 times e to minus pi nx over L. Yeah. So then it is a little bit cumbersome problem, especially to recover this green function from such arguments. But you see first that we actually I forgot to divide by L here. We observe this behavior. We observe this decaying exponentials, which appear because eigenvalues of this tangential part of Laplacian are all positive. Of Laplacian, they are negative. So um, because of this, we have such a behavior, and so what else? Mm, Yeah, so we know that solution should look like this, but in this case we don't need to perform the summation of all these normal modes, although it is doable. We can just say that a given function that we obtained is homomorphic plus anti-homomorphic in all points except this one. It satisfies these boundary conditions, and it has logarithmic singularity at a point y0 in this domain. So it is actually a Lagrange function. Mm. So are there any questions about this? So it was kind of the first problem we solved using this method. Uh, Let us now solve a little bit more complicated version of this problem, where this strip is actually semi-infinite. So let us study this problem. So this is y, this is x, and this is L, This is IL. This is 0. So who can tell what kind of gain function should we have in this case? And can we construct it in some simple way from the function we already have? Only some 0.
We can do the same thing we did before, but
Mhm.
we always put a charge in a symmetric way with respect to the y-axis.
Mm-hmm.
And for example,
Yeah.
the z0 we take positive, in the symmetric position we put a negative charge.
Mm-hmm.
And we do the same computation we did before.
Oh, so we have this charge distributions. Actually, I consider the 0 with 0 real part. So if you write it with positive with some arbitrary real part, we should modify this formula a little bit. So let us write this formula for arbitrary z0. 1 over 2 pi, a logarithm of the absolute value of sine of z minus z naught pi z minus z naught over 2l divided by sine of pi z minus z naught bar over 2l, right? Thank you. Yes. So it is this part. And what kind of terms do we need to add in this case?
I think so. We have this. Basically, it should be sich of pi. Okay, so we add the charges symmetrically.
Yeah, so it should be minus sign here, minus charge here, located at point minus the naught bar, right?
Yeah.
Hmm?
And so when we add those terms, we get like the same green function, only the signs of z0 and z bar 0 change.
Yes, so
Of pi over 12,
two.
z minus z, no, plus z, not plus z0. Yeah.
Yes, and the same in the Okay, so we have this, and now we can simplify it a little bit. So 1 over 2 pi logarithm of. So do you remember what the product of signs is equal to? So it is some function that uh, that vanishes when z equals to z0 or to minus z0, and it has asymptotics at infinity, which is e to the pi over L z. So we can conclude that this is a function hyperbolic cosine of pi z over L minus hyperbolic cosine of pi, so what did I write? Pi z naught over L divided by hyperbolic cosine of pi z over L minus hyperbolic cosine of pi z naught bar over L. Absolute value of this, and here. What? Sorry. So, but we saw such expressions somewhere. It is this formula for the green function in terms of conformal map. Some w of z minus w of z0 divided by w of z minus w of z0 bar. So, and w, and this w is a hyperbolic cosine, right? So it is so this answer suggests us to look at the conformal mapping given by this function, hyperbolic cosine of pi z over L. And so let us do this. Right? So here in this picture, IL 0, yx, this is a z-plane. So and here there is another plane, W plane. So W, so and mapping here is given by this. Z goes to W of Z equal to hyperbolic cosine of pi Z over L. So who can tell what is the image of this ray? Hmm? No.
The real one.
Oh, but so if you take hyperbolic cosine of some big x, so it is some big exponentially big number here. But what happens when x is equal to 0? So what is hyperbolic cosine of 0?
One.
Mhm.
One.
Yes. So from 1 to we get on this half line.
Okay.
And what happens on this interval?
I think it should be like the cosine of pi zero where z is real. So it should be minus 1, 1.
Mm-hmm. So it starts from 1 and goes to minus 1. Right? So and so it is this interval minus 1. And if we draw here some coordinate grid, maybe let us draw it like this. then what will we have? So no, maybe it's not a good idea to draw it this way. Or maybe it's fine. Let me think. No, maybe let me draw it only around this corner, because I didn't think about such a picture. Maybe it's better to draw such pictures in mathematics and not on the blackboard, or first draw it in mathematics and then on the blackboard. Let us draw only some simple part. So if we draw lines like this here in this corner, then we will have this 180 degrees corner. So if you put here 1, 2, 3, 4, 5 rays, then this rays will go like this. So this map around 0 behaves like z squared, because when z goes to 0, hyperbolic cosine behaves like 1 plus z squared over 2. And this map, the square open this angle, turns a 90 degrees angle to 180 degrees angle. So we see it here. And finally, when we come to this point, -1, then hyperbolic sign will be negative, and will go to the infinite direction. So it will be this. So. Yes.
Okay, so it's like a family of semicircle which propagate, which expands. The grid here that should on the left. In the new space becomes like. Okay. Yeah. Okay.
Yeah.
Okay.
So and in all other places it will be just some transformation of the. So if you draw this coordinate grid, it will be still coordinate grid with square cells, but rescaled somehow, because when we perform formal map, then d w of the absolute value squared, or maybe we can write it like, let us write it as a 2D matrix. So dx squared plus, let us write dx times dx plus dy times dy can be written as 1/2 dz tensor dz bar plus dz bar tensor dz. So if we now perform a conformal map, then this dz tensor, so then dw tensor dw of z bar plus dw of z bar tensor dw of z will equal to absolute value of dw over dz squared times dz tensor dz bar plus dz bar tensor dz. So it means that this metric, this transformation always preserves angles, but it can change scale locally. So
Maybe it gets bigger, but the angle stays the same.
yes. So if you draw here some coordinate grid and transform it, you see a deformed coordinate grid, but all lines which were orthogonal originally will stay orthogonal. So maybe I'll send some pictures of this, or you can Google it. So maybe I can send a picture that corresponds to this particular map. And so summary for this problem is the following, that you have at least maybe in total 3 different methods to solve it. So one method is to use normal modes, because here maybe here there is some simpler problem than this problem about the green function. Here we can solve the initial value problem. We can say that this un of 0 are the values of potential on this boundary, and then we solve this problem to find u inside this semi-strip. So here you will just need to compute this sum. So it will be some expression like sum from n equals to 1 to infinity. U e2 minus pi n x over L sine of pi n y over L sine of pi n y prime over L. It will be some green function of y minus y. Yeah, it will be y0. It will be green function of x y y0. Maybe 1/2. No, so with some correct coefficient. So you can compute gain function from boundary to bulk for this boundary problem using this normal mode expansion. Another method is to use this method of images. So we know gain function in the whole space and try to construct it for this half strip, what we did now. And the third method, which we didn't use, but we just saw that this conformal map appears here. It's conformal maps.
What's the general approach for using conformal maps to solve such kind of problems? Like, I impose that the solution should look like that, and then I try to find out.
Yes. And it is so depending on the situation, it is either some art in the sense you need to guess this function, or some science, because for example such a map can be defined in terms of solution of some system of second order equations. Well, people prove that it actually defines this conformal map, and then they need to study this system. So it's for the domains where for domains with boundaries constructed from arcs. And there is another situation which is simple, where we can write this conformal map more or less explicitly. And maybe I'll show a few examples where this is applicable. So maybe I can erase this. Oh. Maybe the basic example is a fractional linear transformation, and we will actually use this to compute one Morgan function. So AZ plus B over CZ plus D. And the main property of this transformation is that it transforms so it maps CP1 in sense complex plane with a point at infinity to itself. And if you want to realize this CP1 as C times C minus 0 factor by a factor by rescalings C cross, in the sense that it is defined by homogeneous coordinates z1, z2. So in this case, this conformal map acts like z1, z2 goes to a, b, c, d, z1, z2. And here we just put z2 equals to 1, which is such a chart where it equals to 1. So, so the main property of this map is that it sends circles to circles. And how to check this? Circle on the complex plane is defined by a condition that z minus some w, maybe z minus z naught times z bar minus z naught bar equals to r, right? Let us substitute this fractional linear transformation instead of z. It will be a z minus b over c z minus d minus z naught. Here it will be a bar z bar minus b bar over c bar z bar minus d bar minus z naught equals to r. So let us multiply by this denominator. So we have az minus b minus z naught cz minus d minus d bar z bar minus b bar minus z naught bar z minus c bar z bar minus d bar equals to r. So it is something of this kind, but now let us see which terms we have here. We have something that is linear, that is bilinear in z and z bar, and we have something terms. We have some constant term and some terms which are linear in the z and in z bar. So let us collect all of them together. So we have a term z times z bar multiplied by a minus c z naught times a bar minus c bar z naught bar, and minus r c bar plus everything else equals to 0. So if you look at this equation, this is precisely this equation up to this constant. So in principle, we can put here some letter a and put it here. So there is ZZ bar, there is ZZ bar plus something linear in Z and something linear in Z bar. So it is. So if you write it in x and y coordinates, it is x squared plus y squared plus alpha x plus beta y plus gamma equals to 0. And it is a circle shifted somewhere.
So these kind of maps, they also move the center, change the center.
Yes, of course. So you can just see where it maps, but it's clear that so it is written that it maps according to this map. No, so center moves somewhere, but it will not be center anymore. So in particular, it is possible that some circle becomes a straight line, because no one told us that this should be non-zero. A straight line is some example of circle also. And so since we know that circles are central circles, we can try to find a map from a circle to from a disk to upper half plane. So this is, so it's the unit disk 1. This is I. Internal part of the disk to upper half plane. So, how to construct such conformal maps is, so what is the usual way? We need to say which point goes to 0, which point goes to infinity, and then we will have some coefficient which defines the overall scale. So in particular, here we see that there is this unit circle, and we can ask which opens to this real line, and we can send this I to infinity. Namely, let us write W equals to Z minus I, and let us send this minus I to 0, Z plus I over Z minus I. So it is some map, and so let us try that it actually maps this unit circle to the real line. So W will equal to e to the I phi plus I divided by e to I phi minus I. When z is on the unit circle, absolute value of z equals to 1. And we are interested in the imaginary part of this w. So to compute it, we need to multiply denominator by conjugate. It will be e to minus I phi minus plus I e to I phi minus I. So, or maybe I can erase this blackboard. we could actually just check the image of 1. Maybe maybe it was easier, but no, let us finish the computation. So in the denominator we will have 1 plus 1 plus I e to the I phi minus e to minus I phi. In the numerator we will have 1 minus 1 from this exponentials plus I e to I phi minus e to minus I phi. So we see that now numerator is purely no, what did they? No. So we see that numerator is actually purely imaginary. So this map should have been multiplied by so by minus I times this minus I because W of 0 then will equal to 2I. Yes, so this gives no, probably it was fine or not. Sorry.
Probably before it was like 2 sine, like with the I.
Oh, so at this moment it was well it was cosine. So, no, sorry, it is fine now. Cosine of phi, 2 cosine of phi divided by 2 plus 2 cosine of phi. So we see that this map actually sends this circle to the real line, and then the question is whether it is upper half plane or lower half plane. So let us see the image of 0. So W of 0 is I. So there is I. So if you draw some small circle around 0, it maps to this small circle. And if you draw some, this external circle goes to the real line. And some intermediate circles which can be drawn here look like this. So they are circles, but of very big radius. And if you draw such radial lines, then these radial lines also become circles that start at I and end on the real line, and they are orthogonal to this system of circles. Like this. Well, there is this conformal map, and this can be used to construct the gain function on a circle. But I actually don't want to do these computations with this conformal map. I would prefer to write the answer just immediately, and then check that it is the answer. And then you can check that it can be obtained using this conformal map. Or in a disk. So we have some point z0, and we have zero boundary conditions. So the idea is the following: that g of z0 equals to 1 over pi logarithm of 1 of z minus z0, 1 minus z times z0 bar. So, and now let me think. Yes, it should be fine. So now, why is it true? Because this function can be written equivalently in the following way: 2 pi I logarithm of 1 minus z over z0 1 minus z times z0 times absolute value of z0. Maybe better to write it. Maybe better to do this for z. Maybe better to do this with the denominator. Sorry, z minus z0 divided by z minus z0 bar inverse, and multiplied by z0 bar inverse. No. No, sorry, again, did the wrong transformation. So let us do it in two steps. So we can make it. We can replace this denominator by its complex conjugate, because we need to compute the absolute value in any case. And on the next step, we rewrite it as z minus z0, z bar inverse minus z0 times 1 over absolute value of z bar. So it's under the logarithm. And now the question: what happens if we substitute z on the unit circle? So we can, if you look at this formula.
write Z equal to EI5, VI5, Z bar, Z bar is equal to ET minus I5, and Z bar to minus 1 is equal to E to the I5.
Yes.
So the fish is equal to 1.
And this is just 1.
Yeah.
So let's log of 1. So,
Which is 0.
yes. Well, this green function actually vanishes on the boundary. And and if you interpret it in terms of this mirror charges, it means that there is a mirror charge at a point 1 over z0 bar. And this is a point related to this one by inversion, because it has the same argument, but a reversed radius. So there is this point somewhere 1 over z0 bar. And so in some sense it is also a method of images, and it's not surprising because this original gain function was obtained by the method of images, and then we just performed a conformal transformation with this picture. But it actually works in 3D as well. We can find gain function in a ball. Okay, so are there any questions about this? Okay, maybe. So there are 20 minutes. We'll study this gain function and its friends later. But in the last 20 minutes, I would like to tell about even a more advanced example of this method of images, which can be applied to the case of okay, so do we need this answer? Or maybe it's better to erase this. So I want to tell about the case where it produces theta functions. So maybe it was kind of let's not label this problem, but there is a problem about some rectangle with this size equal to 1. Maybe better to draw it like this. No, but this size equal to 1. No. Let me draw it here. 0, 1. Some tau, and this tau will be purely imaginary. So it is drawn like this. So it is something purely imaginary. So I want to study this problem to find gain function in such a rectangle. So there is some point 0 with plus charge, and so there is this image that gives point minus z0, it gives point 0 bar. Is another rectangle here. Maybe let me choose this this sizes to equal 1/2 and tau over 2. Yes. So there is 0 bar. Here is a minus 0. Here is a minus 0 bar. And so what else? If you now perform this reflection one more time, we will have the same rectangle with points z0 plus 1, right? Minus z0 bar, minus z0 bar plus 1, minus z0 bar plus tau, minus z0 plus tau. Plus 1, sorry. And if you do a reflection in this direction, we will have the same picture, but well, so it doesn't fit on this blackboard. But it will be minus 0 plus 1 plus tau. It will be minus 0 bar plus 1 plus tau. It will be 0 plus 1 plus tau, and this will be minus 0 bar plus 1 plus tau. So idea is clear, right? That we have such 4 charges, plus plus, minus minus, shifted by 1 and by tau in 2 directions. So there are 4 sublattices constructed from the 0, constructed from minus the 0 bar, constructed from minus 0, constructed from minus the 0 bar. So we would like to construct this green function from the 4 functions which look a little bit simpler. So we are looking for this green function in the form g of z0 equals to 1 over 2 pi logarithm of, so let us introduce in the name a theta function. So it will be theta function of z0 tau, theta function of minus z0 tau, divided by theta of z0, also z minus z0, z plus z0, z minus z0 bar, tau, theta of z plus z0 bar, tau. And this theta of z should be a function that has zeros in this lattice. Right. So it should be a function that vanishes in points of this lattice for n m integers. And I want to propose some answer for this function. Namely, let us write, so it is called Jacobi theta function. Let us call it theta 1, actually. For Jacobi. Theta 1 of z. Tau is sum over integer n's minus 1 to the n e to the pi I tau n plus 1/2 squared plus 2 pi I n plus 1/2 z. So is it okay?
But couldn't we just use the fact that the symmetry of the problem and say that, like, every vertical sleep for every in the grid, for every vertical sleep, we know the green function.
Yes.
So we could just do the sum, the series of those green function, and we get some product of a sinh with respect to x and to y.
Yes, exactly. Yes, of course. This way you will get a product formula for this theta function. And if you equate this definition, that product, you will get a Jacobi triple product.
Okay.
So there will be some non-trivial question about computation of numerical constant, and it will be dedicated the eta function, which is non-trivial, but it is all doable. I just wanted to say that I just wanted to write it in this way because it will also appear for the heat equation in a different context. So, and now let us study the properties of this theta 1. So, who can tell what happens when we shift z by 1? So, how is it related to theta 1?
Not change because it only depends on z as a is multiplied by 2 pi I, so
2 pi I times n plus 1/2. N is integer, 1/2.
okay.
So,
So it gets just multiplied by
It is like itself minus no.
but maybe it's just a series as n over z minus 1.
so minus theta 1, right? So here. Oh. So there is this property. Next question is, what is theta 1 of minus z? So here we will need to flip a sign of n plus 1/2. So it will correspond to n to minus 1 minus n. So that a sign of n plus 1/2 flips, and this term becomes the same. Oh, no, so you can flip this sign to make this term the same. This term stays the same, but there is a minus 1 to the n. So minus 1 to minus 1 minus n is minus. Minus 1 to minus 1, it's minus 1 to the n. So minus 1 to minus 1 minus n equals to minus 1 to the n. So it is minus theta 1 of z and tau. And on this, we know automatically that it has a 0 at z equals to 0. So we know 1, 0. We also know that since it's antiperiodic, it has zeros in all integer points. But it's not enough, because this way we can take the sign function, and it actually is contained here for n equals 0 and minus 1. These two terms construct a sign function. But the most essential property of this theta 1 is its translation by tau. So, namely, let us compute theta 1 of z plus tau. So this will equal to sum over n integers minus 1 to the n e to the pi I tau n plus 1/2 squared times oh, this great computation times e to the 2 pi I n plus 1/2 z plus 2 pi I n plus 1/2 tau. And this is squared. So we would like to rewrite it as a result of expansion of n plus 1/2 plus 1 squared. So we want to obtain it in this way. So let us do this. So this is sum over n integers minus 1 to the n e to the pi I tau n plus 1/2 plus 1 is squared. Then we do the same shift with this n e to the 2 pi I n plus 1/2 plus 1 z. So in this way we get this term which we wanted, but we also get two terms that should be cancelled to make these equations equal. So and what are these terms? So what should I subtract from here? So there will be exponential or something.
Z squared.
No, z squared.
Minus 2 pi I tau n plus n times n plus 1/2.
No. No, wait, we had this term and we obtained it. Minus 2 pi I z? Yes. Thanks. It is. And one term. Hmm?
Minus pi I tau.
Yes, thanks. Okay, so now we simply shift summation index by 1, and this shift by 1 changes the sign of -1 to the n. So here we say that n plus 1 equals to m. So it is a sum over m integers -1 to the m minus -1 to the m e to the pi I tau m squared plus 2 pi I m plus 1/2 squared pi I m plus 1/2 z times e to minus 2 pi I z minus pi I tau. So it is minus e to the pi I tau e to the minus 2 pi I z theta 1 of z tau. So we started from this formula. So well, let me just write it in the end. So it is theta 1 of z plus tau tau. So since it has a 0 at 0, it also has zeros at all points shifted by integers and also shifted by m tau. And it is not periodic as one would expect. It is quasi-periodic and it is not surprising, because it is some. So this function is analytic in the whole complex plane, because this series always converges. It is, and it converges very well. So it is a function in the complex plane that has only zeros, and so in principle, it could have more zeros than just this lattice. But there is a computation that shows that it is the only zero in the fundamental domain. So namely, and there is the following computation. We take some rectangle, for example, of this kind, minus 1, minus 1/2 minus tau over 2, 1/2 minus tau over 2, 1/2 plus tau over 2, minus 1/2 plus tau over 2. And integrate this theta function over integrate d logarithm of theta over the boundary of this rectangle. So let us call this c. So integral over c 1 of 2 pi I d log of theta 1 of z tau. It can be computed using this anti-periodicity properties. So basically, these two integrals will cancel because it is because the logarithm is anti-periodic. So this and this cancels, and we are left with this integral and this integral. So it will be the integral from minus so 1 over 2 pi I minus 1/2 minus tau over 2 to 1/2 to minus 1/2 to 1/2 minus tau over 2 d log theta 1. And another integral is in the opposite direction over this upper part. But we know this symmetry property. So the difference of these two integrals is equal to minus 1 over 2 pi I, the integral from minus 1/2 minus tau over 2 to minus 1/2 plus tau over 2. Maybe minus 1/2 on that boundary times d log of this factor minus e to the minus pi I tau e to the minus 2 pi I z. So what does it equal to? Who can tell this?
But like d log, it means the differential. Okay, so like when log exponential, you get only the exponent, which is linear, so it should be minus 2 pi I dz integrated by between minus 1 plus 2 and 1, and so it should be just minus 2 pi I tau.
But it's a factor.
So just 2.
Why 2?
Then
Minus 1/2 2. No, it is minus 1/2 plus tau over 2, 1/2 plus tau over 2. So difference.
So just 1.
Yes.
Okay.
So and this, and on the other side, it is a number of zeros in the fundamental domain. So this formula tells us that theta function has a single zero in this fundamental domain, and we know this zero. So that's all. We have this nice formula, and we know how to write this green function. So since it is not periodic, oh sorry, I actually forgot to put an absolute value. Since it's not periodic, periodic, we need to check that the green function itself is periodic, but it's not so hard. So. Okay, so are there any questions about this? Okay, so if now, thanks for your attention. See you next week.